So thank you very much for the introduction and for the invitation. It's a great pleasure to be here. Happy birthday, Jacob. Thanks for the pioneering work. So until when do I have 40 minutes, right?
Yeah.
Okay. So it will be very redundant with what has been said before, in particular by Ian Philippe. So I hope it will also be a bit complementary. Yes? I will try to speak up. I don't know. Hello, hello. Can you hear me a bit better? Is it even working?
It's just for the recording.
Okay. Okay. Very good. So I will talk about the free energy of dilute Bose gases at positive but low temperatures. And it's a joint work. It's based on joint work with many people. I think all of them are in the room. Maybe Leo is not here. I did not see him. Leo is not here. So I will follow this plan. I will first try to give a bit of physical motivation, then tell you about the mathematical setting that now you already know all about already, and then I will move to Bogoliubov strategy. You're already expert now, and then I will try to stress a bit more how, the technical part, how to implement Landau's correction, namely the correction that Jean-Philippe talked about to Bogoliubov's theory suggested by Landau. Okay, so the works I would like to present talk about two phenomena. One of them, it's Bose-Einstein condensation. I don't have to remind a lot what it is about. You cool down a gas of bosons, and below some critical temperature, most of them, macroscopic amount of them, occupy the same one-body quantum state. What we are a bit more interested in is the other part of this, the other physical manifestation in this system, which is superfluidity, and which has to do with the particles that are not in the condensate, and in particular, their dispersion relation. So there is this Landau criterion for the dispersion relation for the gas allegedly, the fluid allegedly to exhibit superfluidity. And this criterion is that the dispersion relation is linear for small values of the momenta. So let me remind you that the dispersion relation is the relation between momenta and energy, right? So I exchange momenta P, and E of P tells me how much energy I gained or I lost. And if this dispersion is, if this relation is linear, then Landau tells me that I can expect superfluidity. I just want to go through this argument because it's cute and very easy. So assume that you are in the reference frame of the fluid, and you throw an impurity with a momentum V, sorry. And if you just apply conservation of energy, before collision, you have 1/2 of V square as the kinetic energy of the total system. And after collision, if they exchange the momentum P, then the impurity has kinetic energy 1/2 of V minus P square, and the fluid has gained energy E of P. And now you can just simplify this relation and look for some criterion on E of P, so that this equation has no solution for small values of V. And you find that if the minimum of, or the infimum of E of P divided by P is non-zero, then this gives you a minimal value for the velocity of the impurity, such that the previous equation has no solution. And the fact that this quantity is strictly positive is intrinsically linked to interacting systems, and is not there, of course, for free systems, because E of P is just 1/2 of P squared. Very good. So now that this is said, let's move to the mathematical setting. So we are in the same setting as the one explained by Benjamin. So we look at n bosons in a large box. We are in the thermodynamic limit, in the thermodynamic regime. So the Hamiltonian consists of two terms: the kinetic energy of our n particles and the interaction potential, which is not scaled. And we look at bosons, so we look at many-body wave functions which are symmetric under exchange of their variables. V is assumed to be non-negative, radially symmetric for simplicity, and also compactly supported also for simplicity. Rho is going to be the density, and we are going to look at the regime where rho is small. And that's more or less the only assumption that we will make. And generally, we are interested in two types of questions when studying this Hamiltonian, namely describing the bottom of the spectrum of Hn, and we want to know if there is condensation. And of course, those two questions are connected. If you know a bit from the one side, you can deduce a bit about the other question. I will flash this slide. Since we are in the dilute regime, we expect that most of the energy or most of the what happens will be dictated by two-body events. And as you already have seen, so the scattering length is defined as the ground state energy in this particular boundary condition of two particles, of the two particle Hamiltonian, which is written here in relative coordinates. And if you take f that has boundary condition to be 1 at infinity to be the constant function, and of course you recover integral of v, which is what Bogoliubov had. But of course, if you want to minimize this quantity, there's a more clever choice of f, which is namely when the two particles approach to one another, you want f to decrease, so that the integral of vf square is a bit smaller, but of course you have to pay a kinetic price in the kinetic energy, and as the best way to do it, it is done by the scattering function. So it is true, and this has been proven by Dyson and Lieb and Ingvarsson, as we know now. The first eigenvalue of this operator for large n and in the dilute limit can be approximated by 4 pi rho a. And I will not spend too much time here, but Dyson's idea was to essentially take a trial state, which is the simplest trial state you can construct for an interacting system. So namely, you take this scattering function, and you take the product over all possible couples of particles. As Jan-Philippe said, it is not exactly what Dyson did, but for the sake of simplicity, I think it's easier to write this. And 40 years later, more than 40 years later, Lieb and Jacob proved the lower bound based on essentially the ideas. So Dyson from a lemma from Dyson that essentially replaces singular potential by a softer one, living on larger length scales, at the price of forgetting the price of the full kinetic energy. And modern techniques, they have not departed so much from this idea, but we have implemented this idea in a unitary way to get access to the excitation spectrum. Then there's another ingredient, which is the temporal inequality. So it's the way of Lieb and Ingvarsson to implement perturbation theory. And again, it's not very far from what we are doing now, using condensation to approximate, to localize in the Fock space our Hamiltonian. I just wanted to remind you this, and to go to the next slide, to what is really important to my talk, namely the second order, which is the Huang and Yang correction. So those two screenshots are taken from the paper of Huang and Yang, the one of 1957. And the first one gives you the expansion of the ground state energy in the dilute limit. And you see that the first term is indeed given by 4 pi rho a times the number of particles. And the second term is often referred to as the Huang and Yang correction. Is very specific to quantum systems. Right? So I told you that most of the energy will come from two-body collisions. And in classical systems, in the classical setting, you expect that the next term is given by three-body events. And you would expect here to obtain a rho to the 3 power. And instead, you obtain a square root of rho, which is very unusual and typical of a quantum system again. Now, to understand this correction, it's important to go to 1 or 2 pages later and to look at Huang and Yang predictions of the excitation spectrum. So E naught is just the ground state energy of the system, and E is a typical eigenvalue at the bottom of the spectrum. And what Huang and Yang tell us is that it has this form. So Mk are integers. And so you just pick on your dual lattice that parameterize the momentum, the possible momenta of your excitations in your system. You pick a number for each momentum. And each momentum, if you want to put a particle at a certain momentum, you have to pay a price, which is this dispersion relation. And it's often called the Bogoliubov dispersion relation. You see that it is linear in K, for small k, as long as A, the scattering length of the system, is positive. So going back to the first formula, we see that we have some interpretation of the Huang and Yang term as the renormalized ground state energy of this infinite sequence or infinite collections of quantum oscillators with some specific dispersion relation. Right? In the same way as when you have the typical quantum oscillators minus Laplacian plus x squared, you want to write this as a dagger A with A being x plus gradient or minus gradient. But of course, to do that, you have to commute them and pay a price. And this price is exactly the Huang and Yang correction. So I have to cite the literature. So the first upper bound for the Huang and Yang order was given by Yao Yin. And a bit more than 10 years later, another proof was given by Julia, Serena, and Benjamin. While we had to wait a bit longer for the lower bound, which was proved by Seren and Jan Philippe. And again, now you know that the upper bound for the Wu term, so the next order, has been proven by Maurice, Jacob, Diane, and Benjamin. What I am interested in, again, since we wanted to talk about the superfluidity and the Landau criterion, is the bottom of the spectrum and not only the ground state energy. And if I want to, if you want to look at the bottom of the spectrum, you soon realize that it's close to unfeasible. And the reason is simple. So if I believe Huang and Yang's formula, then the excitation spectrum of the system should look like this. And you see that the spacing is of order L to the minus 2. Where L is the thermodynamic, it's the size of the thermodynamic box, it's very large. And the only thing we are able to do at the moment is to make an approximation on the leading order, which is proportional to n. And we can say something when rho is small. While if we want to have access to the next eigenvalue, we would need to know an order L to the minus 2 smaller of the energy. And this is too difficult, so instead, what we do is we look at the free energy of the system at temperature T, which is defined by the Gibbs minimization principle, and or just by taking minus T log of the space of e to the h divided by T of the. And this is what we did. So we looked at this quantity, the free energy of the system at temperature T. No, there's a problem with the log. No. And we made a similar expansion to the Huang and Yang formula, but for the free energy of the system. And here we go. So we recover the Huang and Yang formula, and we have an extra term coming from the thermal excitations, which agrees with Bogoliubov's or Huang and Yang's prediction for the excitation spectrum of the system. So it really looks like the free energy of independent particles with dispersion relation given by Bogoliubov dispersion relation. So this is the result of 3 works. So we first proved the lower bound with Schlein, who is here, Christian Lam, Robert, who are also here. And we later proved the upper bound with Florian, Christian, and Benjamin with the techniques that I will present today. And later, we also extended the lower bound for the hardcore case with the Copenhagen group, even if not so many people are in Copenhagen anymore. But Søren, Lucas, Theotim, Leo, and Marco. So if we look at this formula, you see the following. You can, of course, approximate the trace by an integral, which I do here. And you can do a change of variable for the momentum p, on the momentum p, to make appear this t to the 5/2. And here I forgot to mention that we are looking at temperature which are of order rho a. And rho a, it's 1 over the Crosby-Tayevsky length scale square. Okay. And that means that we are looking at fluctuations which are of the same order as the ones responsible for the Huang and Yang correction. And especially when T is of this order rho a, we see that the thermal contribution here is of the same order as the Huang and Yang correction. And I think it should be a 3/2 here. So I would like to, okay, I forgot to mention that, so for higher temperature, the second order term is not yet obtained, but there has been first work more than 10 years ago by Robert, and recently the upper bound was given by Yin, and recently Julia, Chiara, Serena, and Andreas, who are here in this room, reproved the upper bound of Yin with more modern techniques using this Bogolubov machinery. I have for the yes, for the Roscoe atom, not for the Huang and Yang. So let me go through Bogolubov strategy again. So it's easier to implement it by writing the Hamiltonian in the periodic setting. So we look at periodic boundary conditions and we write everything in momentum space. And what Bogolubov strategy consists in is to only look at correlations stemming from hard pairs. And by hard pairs, I mean the following: excitations that go in couple and has opposite momenta, so p and minus p, and also terms coming from also this term. And then Bogolubov assumes that he has condensation, so namely that the zero mode is occupied macroscopically. And if you have a mode that is occupied macroscopically, so if you can approximate it by, I mean, if it behaves classically, that means that you can approximate it by its classical counterpart, which is just a real number, so square root of n, it should be square root of n0, the number of particles in the zero mode. And the nice thing by combining, which appears when you combine those two approximations, is that you obtain a quadratic Hamiltonian, which you know how to diagonalize. Because the algebra of what is called Bogolubov rotations is very simple, as Benjamin said it for the file operator. Namely, you can implement Dysons on that, so this product of f xi minus xj in some sort of unitary way by considering this operator. And the nice thing with this operator is that you have closed formula, right? You can compute the action of this operator of this unitary transformation on creation and annihilation operator, and you obtain this relation. So if you implement Bogolubov's approximation, right? So you end up with this Hamiltonian, and applying this rotation, you see that some constant appears here. So ESI is from Erdős Schlein. This is the computation that they made in this article that was mentioned by Jan Philippe. And you obtain some free Hamiltonian here, which almost looks like the formula of Huang and Yang, except that the potential V hat of P should be replaced by 8 pi A with the scattering length. So, and the main issue in today's work are about implementing this correction, Landau's correction, because let's say quadratic correlations are easier to implement because we have a closed algebra, but cubic correlations, or taking into account other terms from this Hamiltonian than just quadratic ones, is very difficult. And this is what I would like to talk about. So if you start from Bogoliubov's approximation, and this is very similar to what Jan Philippe showed earlier, you obtain this approximation for the first eigenvalue. And so V hat of 0, this is the rho square, this is the mean field term. And you get this integral if you replace the trace by the integral for the Huang order. Now, Landau tells you that the physical parameter that should appear in this expansion is A, the scattering length. So you can just substitute it in the first order or everywhere where you see V hat of P. And you see that there is a problem, namely that this integral was converging with V hat of P, but now is diverging as it goes like 1 over P square. And if you just add the diverging counterpart, it corresponds to exactly to what Huang and Yang found. And again, so this is just rephrasing what I said. The issue in Bogoliubov's approximation was it only retained hard pairs, and this missing correlation here is actually hidden in this term, which is cubic in creation and annihilation operators. I mean, forgetting about the zero mode, and stems from collisions involving high moment, couples of high momenta particles, which are not exactly with opposite momenta. So it's minus R, and R plus something which is small, P. And so when they annihilate or when they are created, they create or annihilate not exactly two particles with zero momenta, but one particle in the condensate and one which is close to the condensate. And those pairs of particles are often referred to as soft pairs. And this is this part of the Hamiltonian that we want to diagonalize and which is difficult to do. So in the original paper of Yao Yin, they took some ansatz of this form, which I tried to read the article, but I never managed. So I don't want to enter the details, but it's rather involved. And so a few years later, I want to go to in the Gross-Pitayevsky regime, Bocato, Brennecke, Chinate, Schlein, they implemented this cubic renormalization via some unitary transformation, which in this regime is feasible because it's extremely dilute. And so here I lied a bit in the formula, but I just want to stress that if you are in the Gross-Pitayevsky regime, you see you have the exponential of a cubic operator, but there is some effective prefactor n to the minus 1/2, which essentially kills or compensates for having a cubic operator in the exponential. And if you have this, then you can expand. I mean, you can compute the action of this unitary transformation on observables by using this expansion, the GML expansion. And this extra prefactor allows you to do so because every time not all creation and annihilation operators contract, they are killed. I mean, you can control them by this effective prefactor coming from the extra diluteness, which is there because you are in the Gross-Petevsky regime. And the nice thing with it is that it is a unitary transformation, and we can compute the excitation spectrum, which is what they did in this paper. And as Benjamin explained, if you want to capture the Lee-Huang Yang order or higher orders, you cannot work directly on the large box. You have to localize, because if you localize, and this is redundant, I mean, it corresponds to what I said before, the expectation of those operators Heidegger and A is smaller than in a thermodynamic box. So you have interest, you have some interest into localizing into a smaller subsistence, but there is a cost, namely the cost stemming from boundary conditions. So using some sort of additivity of the energy or the free energy in our case, we can rewrite, we can zoom in and consider subsystems living in a box of side length little l, where L depends on a rho and not on the real number of particles or the real size of the thermodynamic box. And if you want to capture correlations which include the Lee-Huang Yang oscillations, of course you have to take the size of the box larger than the Gross-Petevsky or the Healing-Nance length scale. But for the upper bound, because we don't know how to localize otherwise than by using patching up Dirichlet trial states, we have to take boxes which are much, much, much larger because the Dirichlet localization has a much higher cost than Neumann or periodic boundary conditions. Good. And this is what I wanted to say. So if, yes, tell me. And so at this length scale, L, which is essentially bigger than 1 over rho, you cannot expand using the GML formula because you don't have this prefactor n to the minus 1/2 anymore. And as Benjamin explained, so when n becomes large, the terms in those expansions also become large. So you would have to truncate at a higher and higher order. And what Julia, Serena, and Benjamin did in their paper that reproved the Gaussian upper bound, they considered not a unitary transformation, but essentially the same type of transformation that was used in the Gross-Petevsky paper, but they implemented some cutoff, which is different than the cutoff that Benjamin explained, which has the following interpretation. So they looked at those soft pairs, minus R and P plus R, which have a very large momenta, and they implemented some sort of exclusion principle. Namely, they said, okay, there could be at most one soft pair with whose sum of the momenta is equal to P. And they define this trial state, and they essentially computed the expectation of this trial state divided by the norm, and those cutoff parameters allow them to just expand the unitary transformation, expand via expand the exponential with its series, and compute each term, and in particular recover the correction coming from the norm of this trial state. So in our case, we wanted to look at the excitation spectrum. So we didn't want only to test this formula on the vacuum. We had to test it on the Gibbs state associated to the free system or the quasi-free system that we had in mind. And the quasi-free, so the Gibbs state of the system is a bit more. I mean, it's more complicated than the vacuum, and we had to do something else. So that's our Gibbs state. And so we took this interpretation of this harmonic interpretation, so to say, seriously. We considered each soft pairs as, independent, and we defined this operator BP, which is essentially the same as before, except that now we are only summing over R. So we have this interpretation that there could be exactly one soft pair with total momentum P. And we essentially took the same, a similar cutoff, almost the same as the one in the paper of Bastich and Schlein. And then you realize that, in fact, this operator is nilpotent. So namely, when you square it, you obtain 0, which allows you to, at fixed P, to expand the exponential and obtain a closed formula, as you have for the quadratic case. So we are able to construct a unitary operator that extract the correlation energy coming from soft pairs with a particular momentum P, and we obtain this closed formula. And the only thing we need to do is to just repeat this operation. Diagonalize the cubic part of the operator with this unitary operator that depends on P, but for every P, for every possible soft pairs. And this is how we get the result. And I think my time is almost up, so thanks.